Unigine supports double precision coordinates, enabling you to create really huge worlds. But in the process of creation, you may exceed all reasonable limits and end up having a very heavy application. No matter how powerful your computing system is, optimization is required to maintain high performance and ensure best user experience. To check overall performance while building your worlds, enable the frames per second counter in the Helpers menu, or just hit 0 on the keyboard. Now let's consider a number of ways to optimize your content and squeeze some performance out of it. Levels of detail. Keep the number of vertices and surfaces as low as possible, as it significantly affects rendering speed and physics simulation. Use LODs for complex meshes whenever possible, as they significantly reduce the number of polygons to be rendered. We can prepare several versions of the same mesh with different complexity, details, and show only one of them, depending on the distance from the camera. The closer, the more details. So we select each version and specify minimum and maximum visibility distances in the LOD section of the surface parameters to define when to show and hide it respectively. Now we have a car model with 3 levels of detail, which substitute each other at certain distances, minimizing overall rendering load. We can also make transitions between LODs seamless by checking the Lod Smooth Fading feature in the rendering menu, and then adjust minimum and maximum fade distances. The best way of handling LODs is to have them as separate surfaces of the object. This simplifies node hierarchy and makes LODs visibility adjustment easier. Unigine enables you to create LODs automatically based on name postfixes. You can create and export different meshes for different LODs of your model in a single FBX file. When naming these meshes, add a postfix to specify the LOD each mesh represents. When importing such a model, enable the Combine by Postfixes option. Specify postfixes that you used and set minimum visibility distances. Unigine will do the rest. LODs are combined into a single static mesh with 3 surfaces having specified distances set automatically. Take note that visibility distances affect only visual representation, while collision and intersection are calculated always. It is recommended to use the lowest level of detail for physics simulation, so uncheck intersection and collision for other LODs. Imposters. Substitute mesh geometry with a set of sprites, object snapshots, by using the Imposters Creator tool. Just select the original node, check textures to be baked, and set necessary parameters. Resolution, number of frames horizontally and vertically, and so on. We choose for other object, as it's a car, not vegetation we deal with now. Then specify a folder to store textures. The tool bakes a set of photos of the object taken from different points into a single texture and adds a child billboard object called Imposter that shows one of these photos depending on the camera orientation. So when our object is far away, we can replace it with such a flat picture. No one will notice. Now we adjust visibility distances for the original object and Imposter. Let it replace the original at 60 meters. Use a world cluster for multiple node references. Suppose we've created a complex metal construction using hundreds of instances of certain node references. Each of them takes some time to be drawn. We can reduce rendering time by combining them into a world cluster to take advantage of various optimizations, such as batching. Let's create one by choosing Create, Cluster, Node from the main menu. To combine node references into it, we must make them its immediate children. In our case, we should remove an intermediate tubes construction node. So we select all its children and press Ctrl-Shift-P to unparent them and remove the node. Now we click Create, and all the children disappear from the hierarchy. The number of cluster nodes indicates how many of them are baked into it. Click Expand to access each element. As they are node references, you can easily manage their content and modify all instances at once. World Cluster can also be used to scatter instances of specified node references and adjust each of them individually. Mesh Cluster. All the constructions you see in this oil refinery demo are baked into mesh clusters, as it is the most efficient way of handling large numbers of identical meshes. Mesh cluster has the same purpose as the world cluster, but it is used for multiple identical static meshes having the same material assigned. To create a mesh cluster, we should select a basic mesh for it. Then we place the cluster on the scene. We can add identical mesh static objects as clusters' children and use the Create button to bake them as we did for nodes before. But there is another way. First, apply the same material for all tubes. Return to Cluster Settings and click Collect. The cluster will automatically find and combine all static meshes identical to the basic one and having the same material applied. After that, all meshes are treated as a single one, drawn much faster, and we can easily adjust various parameters like Lod settings for all of them at once. World clutter. When you want to create arrays of randomly scattered node references, you should use a world clutter. It enables you to easily scatter objects across a certain volume, just like this small area with pines and leaves. You can also adjust common density and frequency for each of the node references as well as various placement parameters. Clutters are more memory efficient than clusters, but their elements are placed procedurally and cannot be edited individually. World clutters can be used to scatter non-geometry objects, such as decals, particle systems, etc. Mesh clutter. Mesh clutter is similar to the world clutter, but is used to generate large arrays of identical meshes and treat them as a single one. You can set up materials and LODs, adjust clutter size and other settings, and see the result immediately. Both mesh and world clutters can scatter their elements across the surface of their parent object. Let's scatter trees across the terrain surface. To do so, we simply make the clutter its child and enable Intersection option in the Clutter Settings tab of the Parameters window. This is the most convenient way of creating a forest. You can find more detailed information on creating vegetation in one of our tutorials. Grass Imposter. The Imposters Creator can also be used to generate imposters for a mesh clutter object. It is pretty useful to optimize vegetation. The idea is the same. Render meshes near the camera and imposters at greater distances. This time we choose for vegetation in order to preserve translucency of leaves, and then click Create. Grass object is now used for imposters, and it has the same settings as the source mesh clutter. We make some simple adjustments of visibility distances to make imposters smoothly substitute original meshes. Thus, we increase performance while keeping a realistic look. Occluders. When the camera is close to a big opaque object covering the most part of the screen, like this building, we obviously don't want to render all geometry behind it, as it is not visible and may be too complex. There are several ways of culling unnecessary geometry. We can use Occluders that can be found in the Optimization section of the Create menu. Box Occluder is the simplest and fastest. Place it exactly in the center of the building and adjust its size. Make sure that the Occluders feature is enabled in the Occlusion culling section of the rendering menu. Let's hide the mesh and see how culling works. All objects with bounding boxes covered by the Occluder are not rendered at all. You can see only shadows, which can be removed via the Shadow Culling feature, available in the same rendering menu next to the Occluders. You can take into account back faces of the occluder by enabling the back face flag. A mesh occluder culls geometry using the specified mesh as a culling volume. We can select a specially prepared low poly mesh of the building. It perfectly fits our building and performs culling efficiently without artifacts. But don't use high poly meshes for culling. Simpler culling mesh gives more performance gain. You can use the Occluders helper to view occluders in the world via the small occlusion mask buffer displayed in the upper left-hand corner of the screen. Manual placement of occluders where necessary is the most efficient way of performance optimization. Terrain occluder is the last one. It repeats the shape of the terrain and culls geometry hidden behind it. It is best used for scenes containing a terrain with a lot of significant elevation changes. In other cases, it may even reduce performance. Choose Create, Optimization, Occluder Terrain. Place it in the center of the landscape and adjust its size to match the size of the landscape. Then in the Heights field, set the same map that was used for terrain generation, but downscaled for optimization purposes. Now geometry is culled by the Occluder Terrain. Enable the Occluder's helper to check if occluder matches terrain's shape. Sectors and portals. In indoor scenes, you might need to skip all objects outside the current interior, such as outdoor objects or other interiors. Sectors are designed to split virtual worlds into two areas, inner and outer. Create a new sector and adjust its size to match the room. Now, you can't see the interior from the outside and vice versa. This greatly improves performance, but there's a lot of visual artifacts making two areas look totally disconnected. Portals are used to connect areas divided by a sector. Place one on a face of the sector until it is highlighted with green, and you'll be able to see the interior through the portal. Now adjust portal size to match the doorway. Sectors call all meshes by default. You can make some of them always visible by unchecking the Visibility by Sectors and Portals option. One more portal for another doorway and the whole system looks well. Unnecessary nodes are culled by the sector, while portals restore visual integrity. Hardware occlusion culling. Hardware occlusion test is controlled via the Rendering Occlusion Culling Occlusion query in the main menu. It decides whether to skip rendering of objects, having their bounding boxes covered by any other non-transparent geometry. To visualize occlusion query boxes, enable occlusion queries in the Helpers panel. When such a box is overlapped, it is displayed in red, which means that occlusion test is not passed and the mesh will not be drawn. This test is performed only for nodes with the Culled by Occlusion query option enabled. You can check how this technique works by enabling the second wireframe mode to see all the triangles in the scene. Just type Render Show Triangles to in the console. Hardware occlusion query should be used only for a few objects that use heavy shaders, such as water or objects with reflections. Otherwise, performance will decrease. Keep the number of performance-consuming effects as low as possible. Use the power of bit masking to limit real-time shadows, reflections, physical interactions, and other features. Let's prepare a model of a tree with one extra low-poly surface. We are going to use it to render shadows faster, as rendering them for complex geometry takes more time. Open the current Camera Settings. Here you can see the Masks section. We can filter surfaces to be visible for each camera using the Viewport mask. If the viewport mask of a surface does not match the camera's mask, 1 bit at least, the surface won't be visible for this camera, except its shadow, as you can see, because shadows are controlled by another mask. Shadows from a light source are rendered if shadow masks of the surface and of the material assigned to it match the light mask of this light source, 1 bit at least. Now we need to disable shadow casting for other surfaces, so we simply select all of them and change the shadow mask. Well, the tree shadow is casted by the low-poly surface now, which is pretty accurate and not so hard to compute. Similar approach can be used for dynamic reflections. Let's prepare a low-poly version of a car and hide it using the Viewport mask. Planar reflections double the polygon count, since all geometry in the scene is taken into account by default. This may result in a significant performance hit for a heavy scene. To reflect objects selectively, you can change the reflection mask of the camera to make it render reflections only for certain objects while skipping others. Let's adjust the planar reflection mask. There are no reflections as all of them are filtered out by masking. Well, let's set the first bit of the viewport mask of the low-poly car to use it for reflection. To skip rendering of the low-poly car itself, we should adjust the viewport mask of the camera. Now we apply the corresponding material to our low-poly car and we have a nice reflection of a single car. We can add reflections of other objects of the scene using a less consuming method. Screen space reflections. To enable and adjust it, choose Windows, Settings, SSR. Remember, you always have to find a trade-off between the best visual quality and performance. World layer. In a large world, some groups of nodes may be located far away from the initial spawn point. To speed up world loading and save memory, we can enable background loading of such nodes on demand as the camera gets close to them, or don't load them at all if it doesn't. Firstly, we should save all the nodes of such group to a single node file by dragging the group to the Asset Browser window. Then we create a world layer node. Specify the node file we just created and adjust layer size. We also should specify loading and clearing distances. Let it be 400 meters. Alright, let's check it out. We fly far away from the layer and reload the world. Don't forget to lock the camera to keep its position. Then we start approaching, and at a certain distance the layer is loaded. The distance is calculated from the nearest face of the bounding box. Enable the point option to measure the distance from the center. Switcher. Use a switcher node to simply disable and enable its children at certain distances. Let's set the maximum visibility distance for the interior of the container to 30 meters. Now it disappears unnoticeably as we're moving away from it, giving some more performance. Spatial Trees. Unigine uses separate binary space partitioning trees for frustum culling, collision detection, and other purposes. You can visualize spatial trees via the corresponding option in the Helpers panel. Every time you add, transform, or delete a node, every time you enable physical interactions for an object, etc., you actually modify a separate BSP tree. There are separate trees for different editor node types. These trees divide the scene into regions that are dealt with individually and thus make worlds easier and faster to manage. That's why it is important to enable the Collider Object option for nodes having surfaces with the collision flag enabled, since they're intended to take part in physical interactions, and use Immovable Flag for primarily static objects to move them to a separate tree, optimizing node management. For more details on each of these features and relevant optimization techniques, please refer to our online documentation. Unigine offers you profiling tools for fine-tuning and optimization. The Profiler tool shows general information, such as allocated memory, number of triangles, shaders, and draw calls, so you can view statistics for your scene. It also shows color-coded graphs for time-consuming operations like rendering and physical simulations to make all spikes clearly seen and help you identify problems and bottlenecks. Using these and other recommendations, you can increase performance and maintain stable frame rate in your Unigine application. Remember that failing to use best practices and optimization techniques when preparing your content can slow down any high-performance and well-optimized system.